All right, here's problem 7. The text of it says, every day a flight from Sacramento to Seattle flies directly over my house at a constant altitude of 4 miles. If I assume that the plane is flying at a constant speed of 400 miles per hour, at what rate is the angle of elevation of my line of sight changing with respect to the time when the horizontal distance between the approaching plane and my house location is exactly 3 miles? Oh, so I've kind of drawn this slightly backwards. That's okay. So here's what I've said. Plane flies overhead at an altitude of 4 miles, so this is 4 miles, at a speed of 400 miles per hour. How fast is the angle of elevation changing? How fast is the angle of elevation from me to the plane changing? 3 miles. I should have said before it flew directly overhead. Before it flies directly overhead. So, and actually this is an important distinction, because if the plane is flying away from me, the angle is going to be getting smaller. So the rate of change of the angle of elevation is going to be negative. If the plane is flying towards me, the angle is going to be getting larger. So the rate of change of the angle of elevation will actually be positive. So this actually really is an important distinction if the plane is flying towards us or if the plane is flying away from us. So the plane is actually flying, right? Here's my usual plane picture. Right, the plane is flying towards us. The difference here is that in the way I had drawn the problem before, dx dt, right, the rate of change of this distance would have been positive 400 miles per hour. But now since this x distance is actually getting smaller, this rate of change is negative 400 miles per hour. It's really important with these kind of problems to think about if the thing you're finding is getting larger or smaller. If it's getting larger, its rate of change should be positive. If it's getting smaller, its rate of change should be negative. We also want to find how this angle is changing. So we are interested in finding what d theta dt is. And then our job is to write an equation involving the variables that we want to, basically only the variables that we know how they're changing or want to know how they're changing. So I really want to find an equation that involves this angle theta and this side x and not this unknown side here. So it might make more sense to remember that this angle theta is the same as this angle theta here, right? And what are these called? Alternate interior angles are the same. So this angle and this angle are the same. Or I could also just say, I'm going to draw the triangle here, and this side is still x, and this side is still 4. Either way, we see that tangent of theta is 4 over x. But I usually would like my variable to actually be on top. So instead of saying tangent of theta is 4 over x, I'm going to say that cotangent of theta is x over 4. So there's my equation relating the things that are changing. Cotangent of theta is x over 4. Or maybe even nicer so I don't have to deal with fractions. 4 times cotangent of theta is equal to x. Now we're going to differentiate both sides. So taking the derivative cotangent of theta is negative cosecant squared theta. And then the 4 constant hangs out. Times d theta dt. Right, the derivative cotangent of some stuff is negative cosecant squared of your stuff times the derivative of your stuff. It's the chain rule, or implicit differentiation all over again. The derivative of x is the derivative of x, dx dt. Okay, we're going to plug in what we know, solve for what we don't. We know dx dt is negative 400. And we know d theta dt is what we're trying to solve for. We should be able to plug in for cosecant. So let's see. When I try and find what cosecant is, I have to remember that I'm now looking at the moment when the plane is 3 miles away from being directly overhead. So I'm now looking at the moment where x is equal to 3 miles. Well, if x is 3 and this is 4, normally you would find this side being 5, but we actually don't have to find that here, right? It's not super important. So I know that cosecant, let's see, oh, I do need to know that side for cosecant, right? For cotangent would be fine. For cosecant, we definitely need to know this side. So this side is 5 miles. Let's see, cosecant is the reciprocal of sine. Sine of theta would be 4 over 5. So cosecant of theta is 5 over 4. So this is going to be 5 over 4 squared, which is 5 squared over 4 squared. And now we just have to solve for d theta dt. Notice that the negative signs are going to undo each other. I think they cancel out. So we're going to get that. Let's see here. This is, if I simplify this, this is negative 25 over 4 times d theta dt equal to negative 400. And then multiply those sides by 4/25 to get d theta dt equals, actually negative 4/25. 400 times 4/25. Yeah, is that right? I feel like I made a mistake. No, I don't think I did. Yeah, that seems right. So this is going to be 400 divided by 25. So 100 divided by 25 is 4. So this is going to be 16. That's going to be 16 times 4, right? Because you can cancel 100 here and be left with a 4, and 4 times 4 is 16 times 4. That's going to be 64 radians per hour, right? The rate of change of the distance was miles per hour, so the rate of change of the angle is radians per whatever the same unit of time is. All right, that's it.